And then share screen. Okay. Can you see my slides? Okay, great. So today we're going to talk about indexing. It's a very important concept in database systems. So what you guys have learned on your own last week is that data is stored in files on disk. So everything is on the hard disk, yeah? And the data in a database, so the records are stored in files. Yeah, similar to like any regular file on your hard disk. We learned that there are various file organizations, so unordered, ordered, and hash files. So we looked at the difference between these three types of files. And now we also looked at the fact that retrieving records, so when I type in an SQL query, a select query, it involves reading a set of blocks from disk. That's what physically happens, yeah, to get you the answers of the, or the results of the query. You just retrieve records by reading a set of blocks from the disk. And we know that, right? We mentioned that reading disk blocks is a very expensive operation. So this is really the bottleneck in database system. That's what makes SQL queries slow, is because, right, you have to move things from the hard disk, particularly your database is big or your table is big, to the main memory. Yeah, and this movement involves, you know, a movement of a head, so it's mechanical operation, and that takes time, takes a lot of time. So here's an example, a data file, so a table, right? Let's say a table of employees. It has the name, social security number, birth date, job, salary, and gender or sex. And the records are stored in n blocks. So the first block has a number of records, and that depends on the size of the record, the size of the block. Second block has n records, and so on. Yeah? So overall, you have n blocks. That is the size of this file, and the data is scattered across these blocks. So what is the cost of executing the following query? Select asterisk from student where name is equal to Alain Sam or Alan Sam. Yeah, so basically I have the select statement or select query, and I want to compute the cost of it. How do I compute the cost in database systems? I compute in terms of disk blocks. How many disk blocks would I have to read to be able to answer this query, to show these results in the MySQL, for instance? Yeah, so the idea is to count how many disk blocks satisfy this query that I have to move from the disk to the main memory. And that gives me the cost of executing this query. Why? Because you have a limited time per moving a block from hard disk to the memory, and you can multiply this, you know, constant by the number of blocks. So it's really we measure the efficiency in terms of the number of blocks. That's what we're going to be doing all the time here in this module. Okay. So suppose that, right, you have the record size is 100 bytes. So what does this mean? It means that every one of these rows in the previous slide, so every one of these rows is 100 bytes. That depends, of course, on the number of fields, the types of or the domains of the attributes, and so on. But each one has a fixed size of 100 bytes. Okay, the block size is 1024 bytes. So this is the size of the block on your hard disk. That's a machine specific. So every machine has a different block size. So in my machine, or the machine we're talking about, in which this table is stored, it has a 1024 bytes. And the number of records, so the total size of the table in terms of records is 30,000 records. So this is a normal thing. Yeah, you would have thousands of records inside tables in databases. Okay. Then assuming unspanned organization, what does it mean, unspanned organization? It means that a record cannot span multiple blocks. Yeah, so might have to leave some empty spaces inside blocks because a record cannot fit completely in it, and just move to the next block. So you can't have a block, like a record spanning multiple blocks at the same time. Every record is in one block. That's what I mean by unspanned organization. Okay. So we're gonna calculate few numbers that help me identify the number of blocks that satisfy the previous query. Okay, so the first thing we calculate is the blocking factor. What is the blocking factor? It's the number of records per block. How many records fit inside one block? Okay, I know that the block size is 1024 bytes. I know that I have a record size of 100 bytes. How many of these 100 byte records fit in this 1024 bytes? It's simple, right? It's just the floor of the division of the block size, 1024 by 100. That tells me I can fit 10 records per block. Okay, why floor? Because it's unspanned organization. So I need to really, there is some wasted space, which is, I think, 0.24, in which, right, no record can fit. So I will leave it empty. So I have 10 records per block. Any questions so far? Okay, good. Number of file blocks. So I know that, right, I have 30,000 records, and each block takes 10 records. So how many blocks do I have in total? At 30,000, right? That's the number of records. And I know every block takes 10 records, so 30,000 by 10, that gives me 3,000 blocks. Why 3,000 blocks? Because each block takes 10. If I multiply 10 by 3,000, I get the 30,000 records. Okay, so I have 3,000 blocks. That's the size of the file. This n, right, the n here, right, where we have n blocks, n is in this case, in our example, based on our specs, is 3,000. Okay. Now, I can do two things. I can do linear search if the file is not sorted on the name attribute. So basically, I know that maybe a record like this guy, Zimmer Bayern, might appear here or on top before any a record with a letter that starts with a letter A. So the file is not ordered in any way, particularly on the name, because where condition is on name. Then I will have to do linear search. On average, right, the record will be halfway through the table. So on average, I would need to read 3,000 by 2, which is 1,500 blocks on average. Yeah, because I'm doing linear search. Okay, great. Now, what if the file is sorted based on name? If the file is sorted based on name, like we see in this slide or in this example, then I can do something better than linear search. I can do binary search. So go in the middle and then see whether your record, Alan Sam, is in the upper half or in the lower half, and discard the blocks that do not satisfy. So in this case, right, if I go to the middle, let's say this is the middle, Anderson Zach, I check that Alan Sam is in the upper half. So I can discard all the lower blocks, and I only focus on the upper blocks. And I do again in the middle, and I keep doing this. So a binary search, as you know, from 200 or 211. Okay. So how many blocks would I need to read on average if I'm doing binary search? I have 3,000 blocks. I will do log base 2 of 3,000, which is 12 blocks in average. Why log base 2? Because I'm dividing every time by half. So I'm going to the middle and then the middle, then the middle. So I end up with just 12 blocks on average. So a huge difference in performance. If I had the file was not sorted, I get 1,500 blocks on average multiplied by the time to read the block. And you know this time already from the previous set of slides. So you know that this depends on the seek time, stational delay, block transfer time, and it's in the order of milliseconds. Yeah, but 1,500 times milliseconds, blows up. Versus 12, if I have the file sorted, I would do 12. I would just need to read 12 blocks times the time to transfer the block from the disk to main memory, which is again milliseconds or microseconds. Okay, so huge difference in performance. Okay, questions so far on this calculation? You're gonna use these calculations a lot also in the exam, so please ask questions if you have. Right. So let's move to indexing. What is the idea of indexing? Okay, you have a question. The midterm, the final exam. So there will be a final exam for sure. We don't know exactly what the format will be, but there will be a final exam. Okay. Good. So what is the idea of an index? The idea of an index is similar to a book. Let's say I ask you, find me a page which contains a word, a particular word. What do you do? I mean, you could open, or let's say you have a dictionary, right? And you want to find a particular word. What do? You open the book in the middle, or you go from the beginning till the end, and then start finding the book. So either do a linear search or binary search on the dictionary. Yeah. But I could also have an index. This speeds up operations a lot, looking up something in the book or in the dictionary. How? The idea is the following. Yeah, if you have an index tells you, right, for every word which page it is in. Okay, so I can say, for instance, the word apple appears in page 5, the word hen appears in page 33, and so on. And I could use this index to directly find the page that I'm looking for. So all I have to do is search the index, yeah, figure out where is the word I'm looking for. So let's say it's hen, and then look at what is the page number and directly go to this page number, rather than opening the book or the dictionary and searching in it. Yeah, this saves a lot of time. That's the idea of an index. Okay, the midterm grades, we've already computed them. We're just trying to figure out a way to post them. So the TAs are not able to come to campus, we're not able to meet, so we're trying to figure out a way to be able to post them. We'll see how this happens. The final is not cumulative. No, it's only starting from the midterm up till the end of the course. Okay. So back to indexing. So for instance, right, I can do the same thing on tables. So let's say I have my table, which is the employees table. I can create an index on top of it, which has, basically the name of every employee. So that's the indexing field. And then a block pointer that tells me which block does this record with this value appear in. So I have here all the names are sorted in ascending order in the index, right, in the field name, and then a block pointer that tells me where is the record that this name belongs to. So if I want to find Alan Troy, all I have to do is search the index to figure out what is the index entry corresponding to Alan Troy, and then the record corresponding to Alan Troy would be in the pointer or in the block pointed to by this pointer, by block 4. Yeah, so this is the idea of an index, and I can do this on top of any table, and that helps speed up SQL queries drastically. So this is really something that you should do almost for any table that you create in a real database. The intuition is clear? Okay. So let's see why indices help speed up the queries. So for an index on the name field, so if you do this index, add this index on top of your table, yeah, let's assume that the name field as an attribute was 6 bytes or 9 bytes. So it's let's say a character of length 9. So it's 9 bytes. And assume that the block pointer, which points to the block that contains the record with the corresponding value, was of length 6 bytes. Yeah. So I want to see how many blocks does this index need to store, how much time would it need, or how many blocks would I need to read to be able to locate a certain entry, and in total, how many blocks would I need to read to find the record corresponding to a particular value, to answer a particular SQL query. Okay. So again, the size of the indexing field name is 9 bytes. The block pointer size is 6 bytes. So the index entry, RI, right, I refer to it as RI, is basically 15 bytes. So this guy, a total entry here, a total record in the index is 15 bytes, compared to 100 bytes in the table. Yeah, so this is something we need to make a distinction on. Okay. So what is the index blocking factor? Again, what is the index blocking factor? What does this mean? It means how many index entries can a block fit? Remember that the block size is 1024 bytes. Before, when we were computing how many records of a table fit inside the block, we did 1024 by 100, because that's the size of the record. Now we want to see index entries. How many index entries would fit in a block? The block size is the same. It's the same machine on which the index is stored and the file is stored or the table is stored. So it's 1024 by 15. Why 15? It's the size of the index entry. And that tells you I can store 68 entries per block. So I can store only 10 records per block because the record size is 100, but I can store a lot more index entries because they're smaller in size. Yeah? There's only 15 bytes compared to 100 bytes. So I can store 68 entries per block. Okay. So total number of entries is equal to obviously the total number of records. If you see, for every record here, I have an entry. Yeah? For every record, I have an entry. For every name, I have an entry in the index. So I have a total number of entries equal to 30,000. So how many index blocks do I have? 30,000 because that's the number of entries divided by 68. That's the blocking factor, index blocking factor. That 30,000 by 68, that's 442 blocks. So I need only 442 blocks to store the whole index versus 3,000 blocks to store the whole table. So a huge difference in size. Yeah, the index is much smaller. Now, how do I locate an entry inside the table? Or to execute an SQL query like select star from employee where name is Alan Sam. So basically what I need to do now, I can do binary search on the index. Why binary search? Because the index is sorted. That's the whole point. The index has to be sorted, yeah, to make it efficient to search in. So I can do binary search on the index, and then once I locate the item, just follow the pointer to get to the block that contains the record. Okay. So how much would it cost me to do a binary search on the index? I have logged the number of blocks for the index, which is log 442 blocks, right? That's 9 blocks. So I need to just read 9 blocks of the index. You know, in the worst case, I might even finish earlier, might read fewer number of blocks depending on my query, plus 1 block from the data file to get to the record. Yeah, so in total 10 blocks on average. Whether the file is sorted on name or not, it doesn't matter. With an index, I got to reduce the number of blocks that I have to read drastically, and that speeds up SQL queries very, very much. Yeah, so basically, you have a huge improvement in performance because I read fewer blocks than if I didn't have the index. Okay, questions? Mm-hmm. You don't understand the additional 1 block from the data file. Okay, let's go back to the slide. Okay, so I do a binary search on the index. Let's say I'm looking for Andres key. So I did a binary search on the index. I got to Andres keys, right? This pointer tells me that this block contains the record, which has the name Andres keys. So I need to read this additional block, yeah? Follow this pointer and move this additional block from the disk to main memory to get to this record, because I want not only the name, I want the social security number, the birth date, the job, the salary, and the sex. Yeah, so I have log B to the base 2 plus 1 additional block to read the actual record, to get the actual record. Is it clear now? Yes, the additional block has different size. No, the block is the same. Yeah, remember that the block is the same. It has different number of records. Yeah, and different number of records, and different types of records. But in terms of block size, it's all the blocks are 1024 bytes. Correct? It's just that I'm reading something different, right? So here I'm reading much more. A block here from the index is a lot of entries compared to the table block. The table block would have, fewer records in it, but it's still the same size, reading 1024 bytes every time. Okay, good, cool. So indices are auxiliary files used to speed up the retrieval of records in database. They're really important, something that I highly encourage you to do in any database systems, any database system that you have. Indices are defined on an attribute or a set of attributes, which is called the indexing attribute. So we have something called the indexing attribute, which is what we build the index on. In the previous example, it was the name attribute. Any field or a set of fields can be used to create an index. So you can create an index on any field, whether it's an integer, a string, a real number, it doesn't matter. Any field can be, can create an index on it. There could be multiple indices on the same table. You could have multiple indices per table on different attributes. This is allowed, okay? There are three main types of indices. You have the primary index, clustering index, and secondary index. We'll learn about the difference between these three. We'll also learn about indices on multiple attributes. How can I create an index on composite key, if you wish? How can I create multi-level indices, which are really the state of the art in indexing? And how do I create indices using SQL, and how to use indices in practice? Right? Let's start. So a primary index. The idea of what makes an index a primary index is that it's defined on an ordered data file. The file is sorted physically on disk. Yeah, so it's a sequential file. Okay, so the data is sorted, particularly ordered or sorted on a key field. Yeah, so the column on which the data is sorted on is a unique column. It's the ID, it's an email, something like this. Yeah, so it's a key field, and the file is sorted physically on it, on disk. This makes the index using this key a primary index. In this index, in the primary index, we include one index entry for each block in the data file. So every block, you include one entry on per block. Yeah, which would be the key value for the first record in the block, called the block anchor. We'll see an example in the next slide. A primary index is non-dense or sparse index. Basically, why? Because I don't have an entry per record. So not every record has an entry in the index. It has, every block has an entry, and so thus it's not dense. It's sparse. Yeah, so you don't have. What makes an index dense? If it has for every record an entry. Okay. Let's see an example. So here is a table, our table as before, which has the employee information. Two things we note about this table. First of all, it's physically sorted on the field name on disk. Yeah, so the records appear in this order on disk. Yeah, so really sorted alphabetically based on name. That's the first observation we make. Second observation is that name is a unique field. It's a key field. Meaning what? Meaning there is no repetition. You don't have two employees with the same name. Okay. Hence, I can create a primary index on this table using the field name, because the file is sorted physically on disk using name, and name is a key field. How does a primary index look like? It would have an entry per block. So if you look at the index, it has Aaron Ed, and then the rest of the entries in this block are not stored in the index. Yeah, you move on to the next block, so Adams John, then you move on to the next block, Alexander Ed, then Alan Troy, etc. Yeah, so every entry corresponds to one block here. Yeah? So you reduce the size of the index drastically. Instead of storing an entry per record, you're storing an entry per block. So basically, you're really reducing the size of the index even further. We've known that it's already smaller. It's much smaller because the size of the index entry is just two values or two attributes. But you even reduce it further because you don't store an entry for every record in your. So that makes it even more small. And the smaller in size something is, the faster it will be. You will be able to search it, yeah, because you will be able to retrieve fewer number of blocks than if it was large. Okay, and that's why it's called the sparse or non-dense index, because it stores an index entry per block. Questions? Okay, good. So how do I search it? How do I find the record in this block, in this table? So what do I do? Let's say I want to find Alfred Bob. Select asterisk from the table employee where name is equal to Alfred Bob. I need to use the index, yeah? So I'm going to do a binary search, a modified binary search on the index. I know that this Alfred Bob, right, might not appear. In fact, it doesn't appear in the index because it's not the anchoring record. So it will not appear in the index. So what I need to do is I need to find two records in which Alfred Bob, the value Alfred Bob lies. So basically I'm gonna do a binary search to find the record for which, right, is whose value is less than or equal to Alfred Bob, and then and the value for which, right, is greater than Alfred Bob. So find the two records or two entries inside this table, inside the index, for which Alfred Bob lies. It's between Alexander Ed and Alan Troy. Yeah, Alfred Bob lies in between Alexander Ed and Alan Troy. Then Alfred Bob has to be in the block pointed to by Alexander. So all you have to do is just find the two values that squeeze the value I'm looking for, and then follow the pointer of the smaller value to get to that. That's how it works, searching work. Yeah, so you just find ki and ki plus 1 for which the value is squeezed, and then follow the pointer pi to get to the record if it exists. If it's not there in this block, then it doesn't exist. Any questions about the searching? Okay. Now, what about insertion and deletion? Let's say I want to insert a record in the table, or I want to delete a record from the table. It's very expensive. So to insert a new record, what do I have to do? Remember, the table is physically sorted on the field name. So I have to find out, do binary search, find out which is the right block to insert the record in. So let's say it's this block. I have to, find the right position within the block. So where exactly should I put the record? Then push everything down, and then make an empty space for this record and put it. Yeah, and that involves a lot of reads and writes from disk. So this is very expensive. Yeah, I might have to update the index, because remember now that I'm pushing records, and so the anchors change. So this might not be the first record in this block anymore because I pushed some records. So I'll have to update the index as well. Yeah, so I have to really update the index, maintain the index, and maintain the file in the right order because it's sorted on disk. Okay. If the meeting finishes, I will restart it and you join the same link. Yeah, so it should finish in 9 minutes. Okay, what about deletion? It's the same thing. It's quite expensive. Yeah, I have to locate the record. So I have to do binary search here, find a block for which the record exists, and then delete the record. And then, we have empty space. So I have to, move things up, and I might have to update the index. Yeah. So in general, insertion and deletions are expensive because you need to reorganize both the data file and the index file. Yeah, because both of them are ordered files. Questions about primary indices? Okay, good. Now let's talk about clustering indices. So clustering indices are also ordered data files. So they define, it's an index created on an ordered data file. So the file is sorted based on some attribute, but this attribute is not a key. So there could be duplicate values for the ordering field. So the table is sorted based on some field, and this field happens to have duplicate values in the table. Okay, so it's non-key. If I create an index on this ordering non-key field, it's called a clustering index. And what does it include? It includes one index entry for each distinct value of the field. So I take every distinct value in the field, create one index entry for it. And the index pointer points to the first data block that contains records with that field value. Again, it's a non-dense index since it includes an entry for each distinct value instead of every record. So that's why it's non-dense or sparse, because it doesn't have an entry for every record. Let's see an example. Let's say I have my file, employee. It's sorted physically on disk on the department number. Obviously, the department number is not unique. It's not a key. Yeah, you would have multiple employees belonging to the same department. So I have 3 employees in department 1. I have 2 employees in department 2, and so on. So obviously this is not a key, but the file is physically sorted on the department number. So I have the record of all employees in department 1 before all employees in department 2, and so on. Now the index would look like this that I create on this department number field. It will contain the distinct values for the department. So I have 1, 2, 3. I have 8 departments, or 7 departments in particular, because there's no department 7. So 1, 2, 3, 4, 5, 6, and 8. So only the unique values are going to be the index entries, and the pointers would point to the block which contains the first record with this value. So for 1, what is the block that contains the first record with value 1? It's the first block. For 2, what is the block that contains the first value with department number equal to 2? It's also the first block. If you see, that's the last record. So I'll point to this, and so on. What does that mean? What is the question? It's not the primary key. Who said it's a primary key? I'm saying it's just it's a non-key, so it's not a key. This is not the primary key of the table. Yeah, it's just a field on which I ordered the file physically on it. I can order the file physically on any attribute I want. Okay, so it's not the primary key. No, it's just a field on which I ordered the file physically on. So it can be in this case it's a non-unique field or a non-key field. Is it clear now? It's not the primary key. Explain what, Crystal? Can you be more specific? What I just said, or the whole clustering index? Okay, so clustering field value. Okay, so assume I have a table like employee. It has department number, name, social security number, job, birth date, and salary. What's the primary key of this table? It's going to be social security number. Yeah, it's unique. Department number, is it a key? Is it a unique field? The answer is no. Of course, right? I can have multiple employees in the same department. However, I can sort the file physically on department number. Why would I do that? Because I tend to do queries a lot using department number. So I always want to select, find me the number of employees in particular department, find me the employees in department 3. So I always do in the where condition, I tend to use department number a lot as a field. Yeah, so I do conditions on department number. So it might be a smart idea to sort the file physically on department number. That's what I mean by the file is ordered based on department number. And I can order a file based on any field. It doesn't have to be a key. There's no rule that tells you can only sort a file or a table based on a key. Yeah? You can sort it on department number. There's no problem. What does this mean? It means that the records with department 1 would appear first before the records of department 2. That table would look like this on disk. Yeah, you will find really blocks. If you read the blocks sequentially, you will get records that look like this. Why is 2 pointing to 1? Now let's talk about the index. Yeah, the index you create on this column, department number, looks the following. I take the distinct values. So every distinct, what are the distinct values for this field, the non-key field? It's 1, 2, 3, 4, 5, 6, and 8. So I add these guys, 1 entry per distinct value, and the block pointer points to the block which has the first record with this value. Okay, so for 1, what is the first record with this value in this table? It's this. Yeah, it's this block. This block contains the first record with value 1. Okay, for 2, what is the block that contains the first value for the record with the first value for 2. It's also block 1. If you look at the last record in block 1, it's 2. So I have to say that 2 points to the first block because that's where the first record appears. Okay, good. Yes, absolutely. Yes, Heidi. It's something that you should worry about, and it's something that is no. You have to specify which fields you want to create an index on, and you have to really create them yourself. Yeah. So it's not something that is done automatically. It's something that you have to do. Okay. Good. So for instance, for value 3, what is the block that I should point to? The block that contains the first value of 3, which is the second block. If you see the pointer here, points to the second block. For 4, it's this block. For 5, it's this block, because that's the first block for which the value 5 appears, and so on. Okay? Good. Now, how do I search this? How do I find the record? Let's say I want to find all the employees in department 3. I want to use the index, of course, right? I don't want to do a binary search on the file. I want to use the index to reduce the time or the number of blocks that I have to read. So I can do what? I can do a binary search on the index. That would tell me this is the pointer to follow. And I follow this pointer and I read all the blocks until the next pointer. So basically, I start saying, okay, here's the first block that contains a value of 3, and you have to keep reading until the next pointer. So basically, the pointer, this one. So I read only these 2 blocks. This means that the records with value 3 are going to be in these 2 blocks. Let's say I'm looking for the records with value 5. What do? I do binary search on this block. Okay, that gives me this pointer. Go read this block and read until the next block, the pointer with the next block. So I read these 2 blocks and I realize that this doesn't have any values of 5, so I'm done. Okay, I'm gonna stop now and continue, restart the meeting. Yeah, see you in a bit.